So welcome, we're going to talk about fluid mechanics now, and basically fluid mechanics has a number of things in it. We need to talk about pressure, and then we need to use pressure and talk about this hydraulic systems, like when you go and you put your car on a lift in a auto shop. That's using a principle called Pascal's principle. Some of the car jacks use Pascal's principle. And then that's all static fluid. We have buoyancy, buoyant force, Archimedes principle. Does it float? Does it sink? How much does it seem to weigh? That's all static stuff, which is kind of quite accessible and quite calculable. And then we have the fluid dynamics. And we have fluid dynamics is another issue. Fluid dynamics can be well behaved, and that is if you turn your tap on very slowly and you get that nice stream of water coming out. There could be a straw of glass, it's just perfect. That's well behaved. And then you turn the volume up, you turn the tap up, and it starts to sputter. That's turbulent flow, and that is not well behaved. And traditionally, what the science and engineering community did was they dealt with the so-called well-behaved laminar flow because it mathematically was accessible. And they kind of ignored all the turbulent flow. They'd make prods at it, but the mathematics wasn't there. And so, for instance, anything that involved turbulent flow was a bit problematic. So, for instance, weather systems are turbulent flow. So weather prediction when I was a kid was awful. It was a joke. It was like, if it said to rain, you knew it was going to be sunny, and if it said it was sunny, you knew to take your umbrella. It was awful. Weather, jet engine spotters, so you'd get flame outs on jet engines. Water flow, if you turn up your hose too much, it became problematic. But even things like the flow of blood through your heart can be problematic. And so there was this whole area, fluid dynamics, that was almost like an art. And you could get experience and you could make inferences, but you couldn't do very well. And then, for those of you who heard about chaos theory started being developed. And that has enabled weather forecasting is much more well-defined now. And they have systems where they can avoid flame outs, not just like recover from them, which is hard, but avoid flame outs. And they've even got to the stage where with things like with your heart, with pacemakers, rather than putting a pacemaker in, so pacemakers are put in when your heart goes into defibrillation. It basically, fibrillation means it stutters. And once you get an episode of that, your heart is no longer trustworthy. So there's a tendency to put a pacemaker in. The pacemaker in says, basically, you're an unreliable heart, so I'm going to tell you to pump now, and pump now, and pump now, and pump now. And that's very hard on the heart, which, for the most part, works great. It only had this one occurrence or maybe two occurrences of fibrillation. But because of that, it's like, you got caught doing something and you're on probation for the rest of your life. Just you did one time. You didn't turn this library book back and you never trusted in the library again. They match to the shelf and they match you. And it was just this one-time thing. Because it could happen again, we're not going to trust you with any single heartbeat. But with chaos theory, what they realized is they could sense the onset of a problem. And they could just nudge you away from it and put you back. It's almost like, they can sense when you're going to steal that library book, and they just come up to you and say, don't do it, and you go away. So they only need to intervene every now and then. So it made a huge difference. So in the last, I'd say, 40 years, that's one of the big breakthroughs in science, has been chaos theory. And it's just not made it into the textbooks yet. It's like it takes a while for things to go from being research useful and then application useful. And then it starts getting into the advanced textbooks. And then bit by bit, as people realize they can introduce it in the earlier in the stream of learning, it kind of works its way down. It's not worked its way into our book yet. So we'll look at the laminar. We'll look at the fluid dynamics. We'll only deal with laminar flow. We'll ignore pretty much all the turbulent flow. Cool. So let's talk about pressure. Pressure is force per unit area. Pressure is measured in pascals. A pascal is 1 Newton per meter squared. How do I know that? Well, it's an SI unit. And an SI unit is derived from SI units. So the SI unit for the force is the Newton, and the SI unit for the area is the square meter. So the SI unit for pressure is Newton per square meter, and they happen to name it after Pascal. I counted up one time, there was something like, I got to 12 different pressure scales. And for those who did lab with me on Tuesday, you did a pressure scale pounds per square inch, which it works, but it's just not an SI unit scale. It's not a standard scale. Other common scales are inches of water, millimeters of mercury, pounds per square inch. What pressure is created when an 80 kilogram person balances on a 4 by 4 millimeter heel? Can you have a go at that for me, please? Okay, let's stop that. And let's see what people are saying. People are saying basically mainly A, little bit of C. Let's have a, oops, didn't mean to do that. I guess I got to go back and do that again. Sorry about that. So hopefully they'll come back. So what do? I did my little diagram. There's my mass. There's my weight. I need my force, of course. And my weight is equal to the mass times the gravitational field strength, which equals 80 times 10, because little g is 10 near the surface of the Earth, which is 800 newtons. And my area, well, it's not 4 square millimeters, it's 4 millimeters by 4 millimeters, so it's like a shape like that. So this is 4 times 10 to the minus 3 meters, and that's 4 times 10 to the minus 3 meters. So that combination, multiply the height times the width, is 16 times 10 to the minus 6 square meters. And then my take-home, my principal equation is that pressure is equal to the force per unit area. So pressure is equal to my force, which is 800, over my area, which is 16 times 10 to the minus 6, which would be, I can figure this out, that's going to be 50 times 10 to the 6, which equals 50 mega Pascal. Remember, what is it? Kilo, mega, giga, tera. So there's my answer. Boom, boom. Pascal. Pascal is 1 Newton per square meter. How do you visualize a Newton? If I say to you, hey, show me an object, everyday object that you find in the produce aisle at a grocery store, what do you pick up? Pick up an apple. Newton, apple hit him on the head. Apple is about a Newton. There's big and small, don't worry about it, just, Square meter, a yard by a yard. Get an apple, blend it, spread it out over that square meter. That pressure is 1 Pascal. It's the tiniest amount of pressure you can imagine. It's a tiny unit. Atmosphere, about 100,000 pascals. That's the pressure we have near sea level in the atmosphere. Cool. What pressure is exerted by a right cylinder that has a radius of 2 meters, a height of 4 meters, and a density of 8 kilograms per cubic meter? So now I'm messing with you. You got to work out the area of the circle, and you got to work out the mass of the object, and you got to multiply it by g. And I'm gonna do it because I'm running out of time. So let's do it. Okay. So my mass equals my density times my volume, which equals my density times, it's a right cylinder, so it's pi r squared times h. Agreed? Now, my weight is equal to my mass times g, which equals density times pi r squared times h times g. Okay? And I want to divide that by my area, and my area equals pi r squared. So my pressure, which equals my, my pressure, which equals to my force per unit area, is equal to density pi r squared.
Why are you writing density as P?
It's rho. The symbol for density is rho. Okay? So density times pi r squared times h times g over pi r squared. So my density equals rho g h, which equals, my density is 8 times g is 10, and my h is 4, which equals 320. And I know what you're thinking. You're thinking, hold on, we didn't use the radius. And we didn't, because it cancels out. So, in a test, if I didn't give you the radius, then, would you recognize the fact that it cancels? In a way, by leaving it in terms of letters, I can see it cancels. So that's the advantage. Again, going back, there's an advantage to leaving things in letters if you get comfortable with it. Okay? Consider a shape-shifting object that can change its footprint area but not its mass. A student calculates the pressure that the object exerts on floor for different footprints. That's what's going on. I'm taking the same amount of stuff and I'm just putting it into different shapes. So there's a small area in this one. There's a bigger area in that one. There's a biggest area in that one. What should her graph of pressure versus area look like? Assume appropriate values for the relevant parameters, write a governing equation, make a data table, plot a complete graph. I'm trying to guide you through some things here. So pressure is equal to the force per unit area. And what area? So pressure is equal to the force, and the force is the density, not P, let's make that difference. Not P, it's the density times the volume over the area, which is the density times the height times the area over the area. So,
I don't know what's going on here.
So density times volume, that's force?
so the density times your volume times G, sorry. The density times your volume would be your kilograms. Kilograms per cubic meter times cubic meter is your mass, so multiply that by G and that's your force. Thank you. And then let's have a look. And then we divide that by the area. I'll say. So I'm going to leave that as volume. Okay. I'm sorry, I'm losing my way here a little bit. So I got there's a couple of things I'm not so happy about at the minute. So I'm plotting pressure versus area look like. So there's my pressure. and H times A, and my area goes away. Oh yeah. So that means that my pressure is a constant. My pressure is equal to the density, which is a constant, times G, which is a constant, times H. Ah, okay. Yeah, I'm making a mess of this. It's all right. I'm gonna. I think I'm plotting the wrong thing. I should be plotting my pressure versus my height. So what I'd see if I plot my pressure versus my height, it would be linear, and it would kind of go like that. I know, as I said, I'm plotting the wrong thing. I asked you to plot the wrong thing. So clearly, this is not going to come up on your test.
So just skip this slide?
Yeah. I know, try and figure it out, but don't not do the rest of the stuff because of this slide. It's like, I need to rework it. And asking you to do something on this is not going to happen as well. So that's a doable question. This is, system consists of a right cylinder resting on the ground. The cylinder exerts a pressure of 5 Pascal. What would be the pressure of another cylinder that had a height that was 4 times greater, a radius that was twice as big, and a density that was 3 times greater? So let's do this.
Are we using the formula from the previous slide?
I'm going to figure it out. I have no idea. I got to figure it out. I got to visualize. So basically, what would be the pressure? So I want pressure is equal to the force, which is the weight over the area, and it's a right cylinder. So my force is my mass times G. That's my force times the area. And my mass is going to be my density times my volume times G over the area. Let's put that in that so I know what it is, which equals, now let's have a look at this. What would be the pressure of another right cylinder at a height we're changing, radius we're changing, twice as, and 3 times greater density. Okay, densities we're changing. So then I say, well, density is equal to my volume, which is my area times my height times G over my area. So my pressure is equal to, A's go away, my density times my H times G. So pressure new over pressure old is equal to pressure new over, the old one was 5 Pascal, and this equals the density new times H new times G new over the density old times H old times G old. That's how I do my ratio problems. I figure out what the equation is, and then I put the new over the old, and then I look at my ratios. And the density, does the density change? It says, yeah, the density of the new one is 3 times greater. Okay, I don't know what it is. So I could have 4 and 12, that's 3 times greater. Or I could have 5 and 15, that's 3 times greater. Or I could have 3 and 1, that's 3 times greater. I like 3 and 1. It's the simplest. And my height is 4 times greater. So I could have 16 and 4 or 12 and 3, but why not 4 and 1? And then my G. Do I change my G? I don't change my G at all. Don't say anything about changing G.
What about the radius? Does it matter?
Is it in my equation? So it won't matter. Okay. So that's my next. That was my next big thing. So my G, you can either put down G and divide it out, or you can put down, let's call it 1 and 1 and divide it out. It doesn't make any difference. And so this equals 12. Now, I can't tell you how many people lose points because they give me that as the answer. Because they're not writing equations, but I write in equations. I speak in sentences. I don't say the blue car. I say the blue car drives at 55 miles an hour. I write in sentences. I write in equations. So I know that P nu over 5 is equal to 12. So P nu is equal to 5 times 12, which equals 60 Pascal. There's my answer. So don't lose points because you're just doing all the heavy math, but you're not thinking in sentences. Don't write phrases down. If you're not putting something with an equal sign in, feel uncomfortable because something's got to equal something. Otherwise, you know, we tend to deal in equal stuff. So just tighten up on that. If you're used to writing half mv squared rather than kinetic energy, stop it and put k is equal to half mv squared. Get used to thinking in sentences. So there it is. So that's a typical ratio problem. What about the R? Complete red herring. Give you it just to see if you do something with it. Methodology. You figure out what you want. You look at kind of what you're given. And you develop or you remember. Sometimes you've got to remember, sometimes you develop. But you develop an equation that links what you want with what you've got. And then you do the new over the old, use ratios, and it just falls out. It'll work out. Next little bit. I have a fluid now. So I've gone from solids to fluids. I have a fluid now. And so the fluid will have an ever-increasing pressure as I go deeper and deeper into the fluid. If I'm here, there's only one layer of molecules above me, and down here there's 1,000 layers of molecules above me. So pressure increases with depth. If you're not comfortable with that, imagine getting a silo and filling it with bowling balls. And then you climb in and you get underneath the top layer of bowling balls. It will be quite squishy. Now open the trap at the bottom and climb in under 100 layers of bowling balls. You'd be squished completely. So pressure increases with depth. Density does not. Water is no more dense at the bottom than it is at the top if it's pure water. If it's like saline and all that kind of stuff, yeah, you got a more complicated situation. But H2O has the same density, same packing extent. It's an incompressible fluid. Gases are not incompressible. So the pressure increases with depth below the outer edge of the atmosphere, but density changes. So fluids are different from gases, are different from solids. Consider a body of density rho, which is measured in kilograms per cubic meter. The pressure at a depth h below the surface of the liquid, open to the atmosphere, is rho gh. So I say my absolute pressure, the numerical value, is equal to my atmospheric pressure, what you started off with, because there's an atmosphere there, plus the gauge pressure. Why is that called the gauge pressure? Because they used to use this column of liquid as a pressure indicator. And so you talk about the pressure of the gauge. And so they talk about it as the gauge pressure. The pressure at this point caused by that bit is the gauge pressure. The absolute pressure is the gauge pressure plus the atmosphere pushing down on it. So I say, but P gauge is equal to rho GH. Let's just stop there for a minute. That's kilograms per meter cubed times newtons per kilogram times meters. So if I look at that, that's going to be kilograms goes away, newtons per meter squared, which gives me Pascal. So that makes sense. So P absolute is the absolute pressure, P ATM is the atmospheric pressure, and rho GH is the numerical value for the gauge pressure. And 1 atmosphere is about 101,000 pascals. Okay?
The small g stands for gravity, right?
Small g is the gravitational field strength.
And that's like 10.
10 what? 10 newtons per? Exactly right. Well done. I'm going to draw a line there, and we'll get back to this next time. Okay, I'll see you guys next time.